Okay, we're now looking at page 35, the triangle inequalities. So we've got OA, OB. You know what this is. Tell me what this is. Yes, it's Z1 plus Z2. You can see it there. And we already know that OA minus OB. Tell me which one this one is. If I go Z1 and this is minus Z2 down here,
It's Z1 minus Z2.
so that one's Z1 minus Z2. So Z1 minus Z2. Okay? And we know that that is up there is Z1 plus Z2. So in a triangle, all this has got to do with is that the longer side has to be less than or equal to the sum of the two shorter sides in a triangle. That's what the triangle inequality is. So, for example, if this is 7 and that's 10 length, modulus, or let's make nice small numbers. If that's got modulus 2, 3, and this has got modulus 4, this can't be modulus 10. The triangle wouldn't close. This has to be less than 7 modulus. Because, look, if I go, that's 3 and that's 4, the flattest triangle I could draw is 7. It's trying to draw up a triangle. See, triangles look like that, but if that's 3 and that's 4, this is less than 7 down here, because when I lay the 3 and 4 flat, they form 7. Yeah. So that third side has to be, its length has to be less than or equal to the sum of the two shorter sides. So if I go OA, Z1, Z1's really this. I know this is Z2, but this is also vector Z2. Do you know what I mean? Vector Z2. Okay. This is vector Z1, that's vector Z2. This is also vector vector Z1. This is also vector Z2. One's a position vector, the other one's a free vectors. That's also vector Z1. All right? Now, it says in a triangle, OAC, OC, the length of the longer side is always less than or equal to OA plus OC. We were just discussing that with numbers. But OA will equal OC, but the length of OC will equal OA plus AC if OA and C are collinear or they lie on the straight line. In other words, if the triangle's no longer a triangle, if it's flat. The flat triangle would occur if OC will be equal to exactly OA plus AC when it's a flat triangle. Basically, when it's not a triangle anymore and it's just a straight line. The 3 points will lie on the line. So, for example, if this is A, but then we've got to add the other one to it. B gets sort of added on, that length gets added on, and that's OC. All right? Now, I think you know what I mean. It'll be a flat line. They will equal each other when it's a flat line, when the triangle's completely collapsed. Yeah. Okay? Now, let's just replace that with what each length is. OC, the length of OC, isn't it the modulus of Z1 plus Z2? So when you're talking length of that line, modulus. Modulus. So we know that's Z1 plus Z2. So the modulus of Z1 plus Z2, you can tell me this. Miss, this side has to be less than or equal to these other two sides added together. It will be equal if the triangle's flat. Okay? So, just replacing OC with modulus, its length, modulus Z1 plus Z2, is less than or equal to the modulus of Z1 plus the modulus of Z2, with the length, modulus of Z1 plus Z2 equals modulus of Z1 plus modulus of Z2 when Z2 equals K times Z1. What does that mean? If Z2 equals K, some constant times Z1, it means that Z1 and Z2 lie on the same line. So I'll just show you. If we looked at this, right? So if this is Z1 and this is 2 times Z1, for example, this might be K. So Z1 might be there, but this might represent K times Z1. It's got the same argument, but it's just been lengthened. Okay? So that's the only time when Z plus 1 plus Z2 will equal Z1 plus Z2. It's basically when Z1 and Z2 lie on that same argument when they form a straight line. Remember, they have to be collinear. The arguments have to be the same. One will just be maybe the same length, but possibly a different length to the other. That K could be 1 if I'm doing an isosceles triangle. Like if that length and that length are the same, it's just Z2 will be the same length as Z1. All right, now, so they will be collinear. So there's the first side, there's the second side, there's the resultant. Got it? So there's Z1, there's Z2, and that's Z1 plus Z2. All right? So, now, in the triangle OAB, now what I'm saying here is that this side is less than or equal to OB plus, no. OA is less than or equal to, girls, I have another triangle, don't I? Okay, so I can say this side has to be shorter than these two together, or I could say that Z2 has to be smaller than these two together, or I could say that Z1 has to be smaller, smaller its size than these two added together. Okay, it doesn't matter which way I do it.
Wouldn't it be like equal?
OA, so this side is less than the sum of OB and BA. Okay, so in triangle OAB, second diagram, OA is less than or equal to OB plus BA. They will all equal, OA will equal OB plus BA when OB and A all lie in a straight line again. Okay? Obviously not that size because they're not in a straight line there. So if I replace that now with what I've got there, so what's OA in your diagram? So Z, modulus of Z1 is less than or equal to, what's OB? Modulus of Z2 plus BA is modulus of Z1 minus Z2. So, and then I can rearrange this if I want. They are all positive, all right? So I'm going to take this over. Actually, no, why don't I just take this over there? I'm taking that to the other side. So I get modulus of Z1 minus Z2 is greater than or equal to modulus of Z1 minus modulus of Z2. Can you see that? I decide to keep this here and take that over. Open mouth is facing Z1 minus Z2. All right? With, it will be equal when Z2 equals a constant times Z1. In other words, when they lie on the same straight line, they've got the same argument. Yes.
But then, isn't the other side meant to be? So isn't...
Notice there are two triangle inequalities, one for the addition of sides, one for the subtraction of sides. So Z1 plus Z2 is less than or equal to Z1 plus Z2. Modulus of Z1 minus Z2 is greater than or equal to the modulus of Z1 minus Z2. All right? Okay, all right, let's have a look at this example. Example 9 here. We've got that if Z1 is 3 plus 4i and modulus of Z2 is 13, that's the modulus of Z2. Think of Pythagoras' theorem if you want. Give me an example of how you're going to get 13. You know, good, yeah. 5, 12, 13, all right? Find the greatest value of Z1 plus Z2, modulus of Z1 plus Z2. Okay, we know that the modulus, let's state the triangle theorem, inequality theorem, that the modulus of Z1 plus Z2, in other words, the longer side has to be shorter than the sum of the two other sides. Okay, this is not Pythagoras theorem. We don't want squares, no square roots, all right? The longest side we know has to be shorter than the sum of the two other sides. Now, we know that modulus of Z1 is what? We don't need the argument. Isn't it just 3 square root of 3 squared plus 4 squared, which equals 5? So, which equals, now I'll tell you why I'm putting equals, because what I'm about to write here equals the line above it. But the inequality still holds. Okay, now, which is, so that happens to equal 5 plus Z2 equals 13, which equals 18. So what I'm really saying is that the modulus of Z1 plus Z2 is less than or equal to 18. Is that okay? Because those values are equal to those. So basically the modulus of Z1 plus Z2 is less than or equal to 18. Because I'm just saying, well, that equals 5 and that equals 13. Okay? Now, the greatest value is obtained of the greatest value of 18 is obtained when, you tell me when that line's going to be, if I've got a triangle basically, and I know it doesn't look like, and that's 5 and that's 12, when am I going to get 18 here? When it's flat and it's a straight line. So when Z2 equals K times Z1. It won't be a triangle, that's right. So the greatest value of 18 will be when it's not a triangle anymore, when it's a flat straight line, when you're adding two lines together. When will we get 18? We're not going to get 18 there. 18 will only occur when I've got 5, 13, 18. That's when 18 will occur. So when do we get the greatest value of Z1 plus Z2? When, yes, when they're collinear, when Z2 equals Z1 times some constant. In other words, they've got the same argument and one's just a bit longer than the other.
Wait, what's the constant though?
I don't know yet. So, for some positive real K. Okay, but we know that the modulus of Z2 equals 13, and we just said that that Z2 equals K times Z1. Okay, are we going to work out? K is going to be easy to work out. So we know that modulus of Z2 is 13. So therefore, doesn't 13 equal K times what's Z1? 5. So K is 13 over 5, which is that. Yep. So therefore, Z2 equals, remember how it's a constant times Z1? You know what Z1 is, it's given in the question. So therefore Z2 is 13 over 5 times 3 plus 4i. So you all know that you get that flat, it's not a triangle anymore when it'll add up to 18, and it won't be a triangle anymore, will it? And you know that that's going to be when those two, when they're collinear. So in other words, you know it's going to be when Z2 equals some constant times Z1. Okay, now why did I say Z2 is a constant times Z1? I'll tell you why. Z2 is 13. We know that the modulus of Z1 is 5. So 5 times something gives me 13. Okay, and that's what we're just doing here. All right, so that's why it's not Z1 equals constant times Z2. We know Z2 is longer. All right. So we know Z2 is a constant times Z1. The constant's 13 over 5 times Z1 is 3 plus 4i. Therefore, Z2, if you just multiply, you get 39 over 5 plus 52 over 5i. And that will occur when modulus of Z1 plus Z2 equals 18. If K is real and Z1 minus Z2 over Z1 plus Z2 equals Ki. Where have you seen Z1 minus Z2? It's that's the shorter diagonal of the parallelogram. Z1 plus Z2 is the longer diagonal of the parallelogram. So whenever you see Z1 plus Z2 and Z1 minus Z2 in a problem, the problem can most likely be solved using the geometrical properties of parallelograms, okay? So if K is real and if that diagonal divided by the length, this is basically what it's saying. That the length of the shorter diagonal divided by the length of the longer one equals a constant times I, show that modulus of Z1 equals modulus of Z2. You know what they're asking you to prove? That it's a parallelogram. No, that it's a rhombus. And what do you think this K times I business probably got to do with the 90-degree diagonals? I don't know. All right? That's what it's probably, yeah. Okay, so Solution, show the problem on an Argand diagram. Notice we always put our, let's draw this nice and big. So I like to put the A down here, and let's put the B up here, because you can draw a nice, and this will be Z1, and this will be Z2, and we can draw our parallelogram. Oops, see, it's not a very, well, and that's, you know that this is Z1, that's Z1 plus Z2, and do we know which way? I think it's downwards, isn't it? But if you're not sure, just do a quick sketch down there. The other one's Z1 minus Z2. Okay. And I'll call this OA, call this one C. The other point's C. Okay. Now, so if K is real, Z1 minus Z2 over Z1 plus Z2. So we know that. They've told us that Z1 minus Z2 over Z1 plus Z2 equals Ki. So let's have a look. Z1 plus Z2 is which vector? Which vector is it? OC. And Z1, oopsie, and yep, and Z1 minus Z2 is which vector? Excellent. Now we know we are given that Z1 minus Z2 over Z1 plus Z2 equals Ki. Z2 over Z1 plus Z2 equals Ki, then obviously the modulus of that would equal the modulus of that, and the argument of that would equal the argument of that. So remember when we were going back to that example 6 to prove that, or whatever it was, Z3 equals Z1 times Z2, we had to prove that the moduli were the same and the argument were the same. So if or given that over that equals Ki, therefore we can say that the argument of Z1 minus Z2 over Z1 plus Z2 equals the argument of Ki. Why are we doing this? Argument is just this. It's just that minus this over that angle plus that one, that sort of stuff. All right? Now, wait a sec. Wait, we're going to do it in a minute. So, how do we know that? If this complex number equals that one, then their arguments are the same and their moduli are the same. Okay? Now, so, let's see. We know that the argument, now, as it is a, all right. If K is less than 0, then Ki is less than 0. Therefore, it's a 90 degrees clockwise rotation. Okay? So, look, K could be positive or K could be negative. All right? And if K is positive, we've got a 90 degree rotation anti-clockwise. And if K is negative, Ki will be negative and we'll have a 90 degree clockwise rotation. Okay?
Didn't you say for all positive real K? Isn't that a definition?
2i is pi on 2. And the argument of minus 2i, look, for example, if K was 2, see Ki is up here. What's its argument? Pi on 2. If K is negative, like minus 2i down here, its argument is minus pi on 2. Okay, sorry, that's just the argument of a complex number that is purely imaginary. And the x part would be 0 for this. Okay, now, in other words, what it's telling us is that the argument of this minus that is 90 degrees, either positive or negative 90 degrees. That's what it's saying. So, are we okay with this? So, the argument of that equals the argument of Ki. Ki could be 2i. Its argument is pi on 2. Sorry, the argument of minus 2i, for example, is minus pi on 2. It's just sitting purely on the y-axis. Just the argument. So, let's look at the left-hand side. Argument of Z1 minus Z2 over Z1 plus Z2. Doesn't that equal the argument of Z1 minus Z2 minus the argument of Z1 plus Z2? Now, because this applies, therefore that is equal to plus or minus pi on 2. The argument of that equals the argument of Ki. We've just said that the argument of Ki equals plus or minus pi on 2.
The other example is
Z1 minus Z2 over arg of Z1 plus Z2 is argument of Z1 minus Z2 minus the argument of that. Isn't this just saying that the direction of this minus the other one, if I subtract the angles, basically, their arguments, I get 90 degrees. All right, why don't I draw that other one down here so you can see it? Isn't that the same as this? Look at that. That minus this angle in here is 90. Or that argument minus this one. If you go subtracting these, you're either going to get positive 90 or negative 90. Isn't that Z1 minus Z2? I can draw it down here.
Yeah.
Okay, that's Z1 plus Z2. If I do the argument of that minus the argument of this, what do I get? Well, let's say that's 60 and that's minus 30. What's 60 minus minus 30? 90. Isn't the difference between these 90? It's telling me that if I do this argument minus this one.
I can't see.
But whatever this is, it doesn't matter what it is, minus that. That's a negative angle, obviously. It's telling me the answer is 90. So therefore, they are 90 degrees apart. See, look, I'll show you. I know that's confusing because you're over the x-axis. Watch this. What if I tell you that that's 120 and that's 30?
Then the difference
Well,
will be 90.
That's right. I'm doing the same thing. I know it's in a very awkward position. All right, but it's the same thing. All right, so that minus this, the angle in between, it's telling us the angle, it's been given that the angle between them is 90. Okay, so therefore the diagonals meet at right angles. And so therefore OACB is a rhombus. Why? Because it is we were told that it was a parallelogram with diagonals that meet at right angles. So therefore, if it's a parallelogram, OA equals OB. Therefore, modulus of Z1, if OA, one sec, I'll just move it down. If OA equals OB, because it's a parallelogram, then doesn't the length of Z1 equal the length of Z2? And how do we write that? That the modulus of Z1 equals the modulus of Z2.
I can't see how it's a how they